Hello there. In this video, I want to go over my first ever calculus video. I'm going to do that by showing you how to solve this cubic equation using Newton's method. Now, if you are not familiar with calculus, please leave a comment in the comment section. I'd be happy to do more videos on calculus. I just haven't done them yet. Otherwise, you are proceeding with the understanding that you are familiar with some calculus. Okay? Now, this is the same cubic that I did in my cubic formula video and in my reduced cubic formula attempt video. So to show us what we should get. Now, Newton's method is nice because it is universal. We can do this with any polynomial and really any equation. It doesn't have to be a polynomial. It could be a trig function. It could be an exponential function. It could be a combination of different types of functions. We're just happen to be using it for a polynomial. Okay, and what I'm going to do is I'm going to show you the gist of it first, and then what I want to do is using my digital TI-83 calculator, I'm going to show you how you can speed up this process because it's quite an iterative process and it can be time consuming. Okay, so the first thing we're going to need to do is calculate the derivative of this function. So if we call this f of x, okay, we're going to get f prime of x being equal to 6x squared minus 12x plus 5. Okay. The formula that is used in Newton's method is x sub n plus 1 is equal to x sub n minus f of x sub n divided by f prime of x sub n. So what we're effectively doing is how we start is we pick an x value. You don't want it to be where the function has a derivative equal to 0, because then you just get 0 in the denominator here, and you wind up going nowhere with it, okay? But generally, if you pick out a random number, you should be okay. Odds are you won't get that. So we plug it in here, here, and here, okay? We find out whatever this answer is, and then we loop it. Whatever that value ends up being, we plug it in here, here, and here, and we go until we can see kind of a pattern forming with the decimals and say, you know, generally you do it to 5 or 6 decimal places and it ends up being okay. Now, that's actually the negative of this method is any type of method you use to solve polynomial equations, you can generally get some exact solutions. Maybe not always, but you could. Whereas with this method, while it's universal, you're never going to get an exact method. Okay, the idea is to find decimal approximations. All right, so let's just say, if I recall, the real solution to this was at about x equals 2. So let's start with x equals 2. So x of 2, so my second value will be 2 minus, and now I'm plugging in 2 wherever I see x. So this is 2 times 2 cubed minus 6 times 2 squared plus 5 times 2 minus 3 divided by, now we're taking that 2 and we're plugging it in for x here and here. So that's 6 times 2 squared plus, no, sorry, minus, apologies, minus 12 times 2 plus 5. Okay, so we get 2 minus, we get 2 times 2 cubed, that's 16, minus 2 squared is 4, times 6 is 24, 5 times 2 is 10, minus 3, divided by, okay, so in the denominator we got 6, so that's another 24, minus even another 24, plus 5, and this ends up giving us 2 minus, so we got 16 minus 24, that's negative 8, plus 10 is positive 2, minus 3 is negative 1, and then these will cancel, so we just get 5 in the denominator. So this ends up being 2 plus 1/5, so that is effectively 2.2. Now what we would do at this point is plug 2.2 back in the formula and loop it. So real quick cut, I want to show you my method that I have taught my students at times before on how to type this into your calculator, or if you have some background with programming languages, you probably could generate a spreadsheet or a Python program to do this for you. Okay, so we're working with 2.2. So the first thing I would do in this process is I type 2.2 into the calculator and I just press enter. The reason why I'm doing this is because of the iterative process and the way the calculator works. I'm effectively going to make use of the answer command in the calculator, which will withdraw from the previous result. So let's go ahead, let's get a better view of the formula. So there it is, x sub n minus f x sub n over f prime of x sub n. Okay, so x sub n, wherever I see x sub n, I'm using the answer command. So that'd be second negative, and then I'm going to type in minus. Now, this is where it gets a little weird, and you have to be very precise with this, otherwise it won't work. We've got a polynomial over a polynomial, so I'm going to put in a parentheses, and then wherever I see x in this polynomial, I'm going to use the answer. So that's 2 times answer cubed minus 6 times answer squared plus 5 times answer minus 3. Okay, and we'll close off that parentheses. We're going to go divide by. Now we need to open up another set of parentheses for this polynomial in the denominator. Or open up. It's going to be 6 times answer squared minus 12 times answer plus 5, and then close. Now, do you have to type this in every time? And the answer is no. You don't need to, because at the end of the day, what we're doing is we're going to make use of the recall button. And what this, so let me show you what it'll do. So I press enter, and I get 2.16. Okay, great. So that's a better estimate. Now, if you think about it, if we did this by hand, we'd take as much of this decimal as we were comfortable with and plug it back in and do it again. This can get very tedious, and the more decimals we chop off, the less accurate our answer will be, resulting in more attempts to get an accurate answer. But I don't need to type this in again, because if I press enter, it's going to recall the last thing I typed in, which is this. And because I've made use of the answer command, it's going to interpret that as this. So I'm effectively plugging this 2.16 decimal back into this formula. I'm going to press enter, and I can just keep doing that until, as you see now, I've got 4 decimals in a row. Is it as accurate as it can be? No, it's an irrational number, but this only goes up to 9 decimal places. So there we have a solution. Now, at this point, I was thinking, well, there's 2 complex solutions. Is Newton's method only good for real solutions? And I tried it. Now, maybe I just got lucky with this example. Maybe it doesn't work always for complex solutions, but I think it should. If go to mode and make sure you have one that can calculate complex numbers. I'll go ahead and turn that on right now, and I'll quit. We can use a new guess, and the best guess probably to use is the imaginary number I. So I'll start over with the process and press enter. Now, do we have to type that in again? Absolutely not. I can use second enter, which will recall the last entry, which would be I, but if I do that one more time without pressing enter, it brings back all this. Now it's going to plug in I into our formula, and I'll press I, and you can see as I get more and more decimals, and I should probably actually, let's change it to like 5 decimal places. So now let's go 3. So I can see more of it. I get 0.417 plus 0.720i. Okay, so great, there's one of my complex solutions. Now, if we remember, the complex conjugate theorem says if this is a solution to the polynomial, so will its conjugate. So you don't even need to work through the process to get 0.417 minus 0.720i. Remember that theorem, and we know we've got 2 solutions from this method. Okay? If you have a better way of using Newton's method, please share it down in the comments. Thank you for watching.